Okay, so this is the NMR lab for Chem 114. Really, it should be called like the magnetic resonance lab, because what we're doing is NMR, but the techniques, like Professor Bardeen mentioned in his lecture, apply to MRI. So that's imaging, and ultimately what we're going to be doing in this lab is get a graph of 1 over the T1 relaxation time versus the concentration of the copper ions in an NMR sample. So I'll briefly introduce myself. So I'm Kevin, and my email is kchal003@ucr.edu. Please feel free to send me emails about this lab. I would very much enjoy answering them. Usually when we as chemists think about NMR, and I'm sure when you took organic chemistry you went over this, is we think about like a spectrum that looks like this, where on a ppm scale we get like these signals that correspond to what we call chemical shifts. And the chemical shifts are dependent on the position of, usually we're looking at the spectrum of protons or hydrogens or carbons. Those are usually what we look at. And those depend on their positions of the protons or carbons in a molecule. So that's the vast majority of NMR experiments. An organic chemist is just running down to the big magnet quickly to look at the chemical shifts and see whether they correspond with what they think they actually made. But there's a lot more that goes into NMR. And in this lab, we're actually looking at what we call the relaxation times. And so not every experiment is just you get this spectrum. There are experiments that I do as an NMR, experimentalist, that look at these relaxation times. Although usually what I do is this. Today, just in this lab, we're looking at relaxation times. And there are two types of relaxation times. Those are T1 and T2. To help explain this, I'm going to hopefully briefly and successfully go over a concept that we call the rotating frame. And I'm just going to, a lot of this is what Professor Bardeen talked about as well, so hopefully that lecture combined with this brief introduction can sort of work together and help you understand what exactly we're doing here. So when we put a sample, in this case it's going to be some ions in water, we know that those are made up of many small molecules, and in those small molecules are the particles, are nuclei, and when we refer to those nuclei in NMR, we call them spins. And when they're put in a magnet, all those spins align, basically. So we have a bunch of samples, a bunch of spins, and they're all pointing in different directions, with the arrow corresponding to what direction it's pointing in. Now when we put it in a magnetic field, I'll make it a big arrow, and we call it V naught. All those spins become aligned. Okay. And if we add all of those together, and we put it in what we call the rotating frame, we get all of them pointing in the same direction, now added up. And I'm going to call this direction the Z direction. And what I'm going to do is just draw the 3 dimensions. So this is all pointing in the Z direction. So this is Z, this is negative Z. This is Y and negative Y, and this is X and negative X. It doesn't really matter that this is Y and this is X. You can call this X and this Y, it's arbitrary. I'm just calling them that for our sakes. And so when everything is aligned in the Z direction, we can't detect anything with, we can't get any NMR signal, okay? So everything's aligned, but they're aligned where we can't detect any actual signal. But if we bring all of our aligned signals down into the XY plane, it doesn't matter whether it's on X or whether it's on Y. If there are any spins in that plane, then we will be able to detect it. But it doesn't stay like that forever, and that's where relaxation time comes in. So if we apply a pulse, which we'll be doing in this experiment, a pulse will turn all this magnetization in. Okay, so now all our magnetization is in the Z direction. If we apply what we call a 90-degree pulse, that'll bring it down into the XY field, and then we can measure our NMR signal. So now all of our magnetization is in the Y direction. And then what happens is, it doesn't stay there forever. It always wants to go back to the Z direction. So what happens first is the intensity of the spins in the XY plane decreases first. So there's a loss of XY magnetization. So the intensity becomes less. So that's a smaller arrow. And then what happens is that magnetization returns to Z. And this, very basically, is the pulse acquire experiment. So that's kind of the basic NMR experiment. In reality, these final steps, the loss of the XY magnetization and the return to magnetization along Z at equilibrium, actually happen at the same time. However, the loss of XY magnetization occurs so quickly that I just consider it like this. Like, that happens first and then we return to Z. And what those two different things are our relaxation times. So the loss of XY magnetization is T2. T2 relaxation, or spin. So spin, T2, those mean the same thing. And then the return to the Z magnetization is T1, or spin lattice. So the pulse acquire experiment is not just like the most common basic sort of NMR experiment, it also forms the basis for other more complicated experiments. So a lot of these put together constitutes like more complicated 2D or 3D experiments, or like we're about to see experiments that will let us measure recovery time. So like I said, it's important to keep in mind that T1 is much greater than T2. So that the XY magnetization is lost before the Z magnetization returns. And it takes about 5 times the T1 time to return 99% of magnetization. So it's very common to put in a sample, do an experiment to measure T1, and that will allow you to determine how long you actually have to take between applying your pulses, because it'll be 5 times the T1. Because if you wait less than that, the magnetization will not have fully returned to Z, and the amount of signal you get for your experiment will be less than it should be than if you waited the entire time. And we'll see that in the experiments that we do today, that we wait some time between the pulses. Okay, so that covered T1 versus T2, and I'm gonna erase some of this to make space. So there is a problem, though, in general with experiments involving magnets, is that a magnetic field is rarely perfectly homogeneous. Like, depending on the quality of the magnet or where your sample sits in the magnet, it's not going to be a consistent field. So we always have to contend with the inhomogeneity of the magnetic field. And you'll see in this lab and in the lab manual, there's also something called T2 star. It's better not to think too hard about it, except to understand that T2 star takes the field inhomogeneity of the magnet into account. And there's also experiments that we can do to help us get rid of the effects of that inhomogeneity. Okay. So the main experiment we're going to do in order to get our T1s is called the inversion recovery experiment. So using that same idea of the rotating frame, we always start with our bulk magnetization along Z. This time, instead of applying a 90-degree pulse, we'll bring you down into the XY plane. But instead, we're going to apply a 180-degree pulse. And what that does is it brings us all the way down to negative Z. That's still within Z, so we can't measure any signal along Z. Still, we're only going to be measuring in the XY plane. So now we have our magnetization along negative Z. And now we have a delay that we call tau. So that's just some amount of time. And this amount of time, tau, will cover some of that T2. So that's decreasing the amount of magnetization here, but not so long that it returns to positive Z. So we're just decreasing the magnitude of that arrow. And then we're going to apply a 90-degree pulse to bring that amount of signal into the XY plane. So now we can measure that signal. Then after that, we can acquire and measure the T1, and what you'll get is something that looks like this. We're going to be doing this experiment multiple times and changing the tau and measuring the signal that we get. And so that so we're going to, depending on what the tau is, that will determine whether your signal is negative or positive. So if we have at very, very short taus, taus that are close to 0, we'll get negative signal. As we get higher, we'll get a smaller negative signal. At some point, we'll get no signal, and then we'll get a slightly positive signal, and then a very positive signal. Where there's no signal, we call that tau null. So that's this amount of time, tau, where no signal is produced, and that will help us determine the T1 time. So that once you get to tau null, the process to get the T1 relaxation time is outlined in the lab manual. So I believe that's one of the calculations you'll have to make in order to find T1. Okay. So that covered inversion recovery. So the next experiment is the echo experiment. So the purpose of the echo experiment is to refocus the field inhomogeneity. So that will help us get rid of the effects of the inhomogeneity of the magnet. What we'll also do to get rid of those effects is what is called shimming. So if we have bad field inhomogeneity, we might get chemical shift signals that look like this. If we have good shimming, we get a nice sharp signal that we're used to seeing from organic chemistry. And so this is a result of poor shimming or bad field, This would be good shimming. So if we shim well, it should look like this. However, even with good shimming, there's some contribution of T2 from the magnetic field, which can be removed by the spin echo experiment. So the spin echo experiment, I'm not going to draw the rotating frame model for it, because I don't think it's, once you have like a basic grasp of it, it's not so important to draw it out, but just understand what each experiment does. And essentially what this experiment will allow us to do is to measure the T2. So, and what the lab manual outlines is we do a 90-degree pulse, we wait a certain amount of time tau, we do a 180-degree pulse, and then another time tau, and then we acquire. And what we end up with is As we increase the time tau, the signal goes down in the XY plane, and we end up with something that looks like this. And that shape is e to the negative t over t2. So plotting the magnetization in the XY plane against t, which is just 2 times the tau, each of these taus that we're adjusting as we do different experiments, will result in a curve that can allow you to extract the T2 relaxation time. Okay, so that's also a part of this experiment, and being able to understand and measure the difference between T1 and T2 leads to what we're doing here, where we're plotting T1 using the inversion recovery experiment against the concentrations of the copper ion. So this is due to that the presence of ions in a water solution decreases. It decreases the T1 relaxation time, which means T1 occurs quicker. But does not affect T2. And that's also outlined in the lecture, and we'll see that with the experiment, that as we are adding more ions, the T1 relaxation time will decrease, but T2 should stay the same. And I know that that's a lot of information, but again, this is online, the lecture is online, the lab manual is online. So if you're unsure about that or what exactly I mean by certain things, please feel free to email me or Zoom me during my office hours, because I can go over a lot of this stuff easier that way. And I think we're ready to get started on some of the experimental things. And so, yep, that's it. Okay, so I'm going to be following the lab manual very closely, because there's a lot of like specific where we're plugging stuff into and where it's going to. So the 4 parts of our spectrometer is the magnet back here. This is, I would call it a small magnet, but it's probably pretty big than like a normal magnet. It's a 21 megahertz magnet. If you've ever done like NMR spectroscopy before, like at our facilities here, the smallest one we have is a 300 megahertz magnet. So when you're at like an NMR facilities, that's why the magnets are so much bigger. They're much more powerful. But this is just 21 megahertz, and that allows us to do experiments on a desktop. Okay. Then we also have the mainframe here, the PS2 controller, not a PlayStation 2 controller, which I thought it was going to be, which would have been interesting. And then we also have the oscilloscope here. So on the mainframe, we have the receiver, synthesizer, pulse programmer, and the lock-in field sweep. That last lock-in field sweep we're not going to use. And I'm just going to check to make sure that all our connections are correct, because I don't know here who was here before I was. So we should connect on this synth. We have pulsed RF out. So on the synthesizer we have the pulsed RF out. Pulsed RF out. Okay, so that's here, and that goes to pulsed RF in on the receiver. And then on the pulse programmer, we have this Q to Q on the synthesizer. And then also on the pulse programmer, we have I to I on the synthesizer. And then we also have blanking out on the pulse programmer to blanking in on the receiver over here. And then we also have on the pulse programmer the sync out to the trigger on the oscilloscope that's over here. And then on the receiver we have ENV out here, and that goes to channel 1 on the oscilloscope. And then also on the receiver we have Q out, and that goes to channel 2 on the oscilloscope. Okay. And then we're going to check that all our switches are correct on the mainframe. So on the synthesizer we have CW out, so that is off. We have on the pulse programmer, we have, yeah. Okay, so on the synthesizer, we're going to turn CW out to off. On the pulse programmer, we're going to turn B pulse to off, and also on the pulse programmer, we're going to turn MG to off. We're going to toggle where it says sync to A, and then also where it says pulse to A. So that should be on. And on the synthesizer, we're going to turn ref out to on. And we're going to set this filter TC to 0.01, so that's already set. Set the gain knob to 0.75, that's also already set. And on the receiver, toggle band to P for proton, and toggle blanking to on, and the width knob to 75%. There's no marking on that, but I'll assume it's already there. And then we're going to turn the spectrometer and the oscilloscope on. So on the this is on the back, a big switch, and on the oscilloscope it's right on the front here. So on these experiments, all we have to do is adjust the synthesizer and the pulse programmer. So in order to, for example, on the synthesizer, to select the parameter, we move the knob. So if I want to select the frequency, I push it down, and then select the digit I want to change, push it down again, and change it to what I want to change. So I want the frequency to be 21 megahertz. So I set it to that, push it again, and then scroll all the way to the arrow and push to get out of that. So then I can go back to selecting the parameter if I need to. Okay. So right, so on the pulse programmer, we have the length of the A pulse and the length of the B pulse. So when I was talking at the board and I said like 90-degree pulse, well, we don't actually set, like, we don't put in like 90 degrees and that's what the pulse is set to. We actually have to adjust how long the pulse is, and that'll determine how far the magnetization moves. So we'll see when we set the 180-degree pulse how we can determine how long our 90-degree pulse should be. And that will depend on a bunch of factors. That depends on your sample, the magnetic field, the instrument you're using, stuff like that. Then we also have this tau. So that's the tau that I was talking about on the board. That's the time between our pulses. And then n is the number of B pulses. So that's like the second pulse in our experiment. If we do a 90-degree tau, a 180-degree. So that's the number of our B pulses. And that's usually 1, because usually we just do a pulse, tau, another pulse, and then we repeat the experiment. And then P is that time between the pulse sequences. So, like I was saying with the relaxation times, that's critical to get correct, or else you won't get maximum signal. Okay. And so the sample we're going to be using first is just distilled water. So I already prepared it. And you can see that there's a very, very small amount of water in our little NMR tube, just about 5 millimeters. And also this O-ring at the top is positioned so that when we put it in the magnet, the correct amount of the tube is in, and the sample should be as centered in the magnet, the solenoid in the magnet, as it can be. And now I'm going to put it in the magnet. So can we do it so it's like filming over the top? Like, so you can see it like being put in.
Oh, you mean?
Yeah, so it's like over top. I don't know if we can't do it, then we can't do it. But
You just cut this part out?
yeah. Do you see like the inside of it? So when we put it in, there's a hole in the center, the only hole that will hold this, and we just put that in. And that's inserting our sample into the magnet, and that's what we're going to be doing our first experiments on. And that's it. Okay, so now that our sample is in, we're going to connect the magnet to the mainframe down here at where it says sample. All right. And now what we're going to do is basically we're going to be doing the pulse acquire experiment. We're going to apply a pulse and then watch the signal decay on the oscilloscope. And we're going to apply an approximation of that 90-degree or pi over 2 pulse. What we're also going to be able to do here is this will also help us shim the magnet to decrease the inhomogeneity. Okay, so I'm going to set the period time P on the pulse programmer to 5 seconds. Alright, so that means that gives us a nice long time for our system to come back to equilibrium between each pulse that we apply. But what that also means is that the experiment only repeats every 5 seconds. So as we adjust our parameters, we should wait until we see that change occur on the scope, and then adjust again, and we'll have to wait another 5 seconds to see how that affects the signal on the scope. I already set the frequency here to 21 megahertz. And yeah, so now we're going to go look at the scope. So
very briefly, you want to make sure that all of your settings on your oscilloscope match your experiment, like so your sample frequency, the impedance of the signal that you're looking at, and make sure that you're also bringing up the channel that you're trying to look at. So the first thing we need to to check. It's the number one thing that can go wrong in all oscilloscope experiments, and that's going to be your trigger. So the trigger menu is right here on the third column. And then we're going to first see who our source is, and we're going to choose external, right? So we can make sure our external is plugged in. If we read our oscilloscope, we see that it wants to accept a 1 mega ohm impedance. And so you can think of impedance as just the equivalent resistance that an AC voltage feels. So if voltage is equal to its current times its resistance, or in our case its impedance, with a higher impedance we should have a higher voltage and a higher signal. For very weak signals, you're going to want to use a large impedance. For very strong signals, like say fluorescence, or the signal response you get out of a photomultiplier tube, you're going to want to use a 50 ohm termination impedance. So we're going to check external. We're going to make sure that our hold off is correct and that we're sampling it normally. And let's see, the last thing we want to check is our level. Make sure, so the level is just the threshold at which the oscilloscope will say, once I've hit this certain voltage, I will accept this as a signal for triggering. Anything below it, it ignores. Everything above it, it accepts. If your level is set too low, you're going to be triggering more often than you want. If your level is set too high, you might not trigger at all. You might not see anything from your experiment. So, all right. Now, if we go to auto and we just don't apply the external trigger, you can see the scope is feeding back in real time. And so every approximately 5 seconds, you'll see a peak show up down here. But we want to be, that is our entire experiment, is that peak. We want to make sure we can see that at all times. So we're going to run back into normal. And now it'll only update the oscilloscope every time it's been triggered. So every 5 seconds it will update. So we're looking right now at channel 1. So we go to menu off. We're going to check the first column and click menu. We're going to look at our input signal. We want to make sure that we're measuring a DC signal. And then down here you've got the impedance, your omega. And we have it toggled to 1 mega ohms. If we did this to 50 and we wait our 5 seconds, we'll see that our signal to noise has drastically dropped. Can't see anything at all. So, very important to make sure that that's working. All right. So the last thing is you can adjust both the vertical offset. So you want to just bring this down to where it's legible. I'm going to go down to where we have our original marker. You can also move this left and right. Somewhere around the first 20-ish% of time, we're going to want to make sure our peak sits at, just so that we can see both the start and the decay. You can also play with your time scale. Again, and then wait the 5-ish seconds. But if your time scale is too short or too long, you won't see your signal at all.
Okay.
I think that's all I have to say about this.
Okay. So I'll go back to the pulse.
Is 100 microseconds what we were using?
Okay, so you'll notice on the oscilloscope that we just have a very small amount of signal. The pulse length of A right now is set to 0.02 microseconds. That's extremely short. So if you think about the 90-degree pulse should bring down all your signal at Z into the XY plane, and we should be able to measure all of that. A pulse that is too short, like this one, 0.02 microseconds, that is probably the equivalent to, like, I don't know, a 5-degree pulse. So only a very small amount of magnetization is in the XY plane, and that's why we get a very small amount of signal. So what I'm going to do is change the pulse length of A, and we'll see that as we lead up to whatever the actual 90-degree pulse is, we'll get a maximum amount of signal. If I go over the maximum, then we're over 90 degrees, and some of our signal from that pulse will be, again, outside of the XY plane, so it'll result in a less amount of signal. So we'll see as I increase the length of the pulse, I'm going to go to, 1.5 microseconds. The signal increases. I'm going to go to 3.06 microseconds. Okay, it keeps increasing. to 4 microseconds. It keeps increasing, and I'm going to use this knob to just keep track of where that maximum is based on the cursor. 5. 6 microseconds. And I'm also waiting a little bit of time because it takes 5 seconds for the experiment to repeat. Oh, you can do that.
That's okay.
Okay, so I'm gonna go to 7 microseconds. And as we get closer and closer to the actual 90-degree pulse, we're going to see that it becomes pretty insensitive. Like, as we approach it, it's gonna be pretty minutely. So now if I go to like 9 microseconds, we can see it decrease a little bit. I'm gonna go to like 10.5, way over, and we see it decrease a lot. So I know that it's somewhere between like 7 and 9. So if I go to 8.56, that's pretty good. It's still lower. And I found that it's about 7.2. But also, like pretty much anything between 7 and 8 is about in the same range. So maybe this isn't exactly a 90-degree pulse, but maybe it's like an 89-degree pulse. That's pretty good. You just don't want something that's way too small or way too big. And we'll also see when we measure a 180-degree pulse, that's usually how we determine what the actual 90-degree pulse is. So we'll get into that with some of the next experiments. So once we have the maximum signal, now we can shim the magnet. So that's up here on the PS2 controller. And inside the magnet is this coil or solenoid. And we're just making very minute adjustments to that in order to get rid of the inhomogeneity of the field. So I previously shimmed it, but we can see like what we want is like a nice long decay. So if I adjust the Y parameter, we can see that that starts to push this out and gives us a longer decay to look at. So shimming is not an easy thing. It requires a lot of adjustment. Luckily here, it's not super sensitive, so we can only mess up the shimming so much. And if it's not perfect, that's okay. So if you were able to do this experiment, you would be able to just mess with this and see how long you can get that decay. And similar to the pulse length, if you go over what the proper shimming should be, the decay will get smaller. So there's like a precise spot that you want to hit. And it's just trial and error. Keep messing around. Until you get something, until you feel like you can't really improve the shimming anymore. So I feel like I've done all I can with the shimming, so now I'm just going to take this signal and save it onto my USB. So going to push the save recall. Hit save waveform channel 1. Okay. Save to file on right. And spreadsheet file format, it's already in. And then save channel 1 to selected file. So it's going to bring up this stuff on my USB and put it in a new folder. Okay, it'll take a minute.
While this is saving, something we also didn't talk about earlier was what I was messing with while Kevin was shimming in the Y direction. The cursor's up here that you toggle with select, or you turn on or off with cursor and it'll bring up a menu. That's going to be your best friend when you're changing different parameters. If you want to see, okay, how much did the height, did the amplitude of my signal change? How much did the width of my signal move as I was shimming or changing the pulse length respectively?
Doesn't want to save.
Doesn't want to save now? It's just a text file, it can't be that large.
Well, we did it before. I don't know why it's not coming up.
Is it trying to save? Does it
Yeah,
have
maybe.
overwrite permission?
Yeah, I'm not sure. That might be the problem. Oh, okay, it just popped up as soon as I took it out, so that's fine.
That sounds about right. So yeah,
Yep.
we have to.
Okay.
Two files, spreadsheet. Probably have to bring up the whole directory first, and then it'll let you toggle save.
I think it's because I already have it on there. That's my guess.
I think so.
Yeah. Because it did not take this long last time.
Go clear the previous name spreadsheet.
Yeah.
You know, it should. Yeah, that might be why. But here, let's go back to save channel 1 waveform. And
There we go. Okay. So save to selected file. And this will take a minute. You can see all my folders. Okay. And then this file will be posted on iLearn along with this video. And that's it for experiment 1.
is my email ID. You can email me as well. So I'll pick up where Kevin stopped right now. As you just saw, like what you just saw was a signal like this, the water signal, and this is the envelope. This will tell you what is your T2 relaxation or the spin relaxation. Now where does this signal come from, or how does it come from? Oh, how does it come from? So if you see, like, let's go back, there's this magnetization along the z-axis, z cap. This is your xy plane. Okay, so in the initial phase or the initial time, you have applied a static field V naught along the z cap direction. So what it's doing is that all the spins get aligned along the z direction. Now the next step is to apply a pulse, like a 90-degree pulse. This pulse can be applied along any direction, x or y. What it's going to do is it's going to bring it to the transverse plane or the xy plane. So at that time it brings it here. So what's happening here is like this, at this point in time, you have to put it down. Okay, so at this point in time, magnetization, all the spins are along the x direction. So if your receiver coil is placed over here, it's going to detect, and at that time your signal is going to be maximum. So like after a certain time, like here, let's say, where is this? So let's say that before this time there was no detection, and then you suddenly see a detection. So this is the time where this is maximum. So as there's time, as the time decays, or as it takes longer, so the spins are going to spread out. So as they spread out, this magnetization is going in different directions and not just concentrated here. And this time taken will be called as T2. So as they are going like this, at the same time along the z direction, they are also going like this. So what it's essentially doing is that it's giving you a projection. So at this time, for example, if the spin went from here to here, so you're seeing a projection along the x-axis and a projection along the y-axis. So this is how, now as you see projection, the projection at initial phase was higher. Then as these spins are going here and rotating and going towards the z direction, this projection is going to become smaller and smaller and smaller and will completely move to the z direction. The time it takes to go completely from the xy plane to the z plane, that's called as the T1 time, and this will go like this. So what you observed here was this, like in the signal which Kevin just showed. So the rate of decay is tau, which is 1 over T2. This is the rate of decay of the FID. So the signal S of T is a sum of the magnetization along the x-axis and the y-axis. So when the spin is going here, it's going to rotate. So this rotation is called as omega. So that is also a Larmor precession, and this can be given as cos omega t because it's along the x-axis, x direction, plus sine omega t. But since it's along y, there's a iota which comes here, and so the form reduces down to S of t is equal to I omega t. So this is what gives you your the oscillatory part of the signal, and this is your decay. So the signal can then be written as, let me just erase this part. Minus I'm putting here, that's because of the phase of the angle or the pulse which has been applied. It can be applied along the negative direction or the positive direction, and the sign is going to change accordingly. So this is your signal. This signal is then Fourier transformed to give you a peak. So this peak will be located at omega. This is the real part of the signal, and the imaginary part of the signal is given like, sorry, the imaginary part is given like this. So at this point there's omega. Okay, so I think you already have a good idea of how to visualize the magnetization transfer, a change taking place from transverse plane back to the z-axis. And now I will just briefly tell you how the equations work. So what you had is the angle beta, this is the flip angle. So mx m naught sine beta cos omega t, my is m naught sine beta sine omega t. This was your Lombard precession, and this is your flip angle. So for example, when you apply a 90-degree pulse, your mx is going to go to m naught cos omega t, and my is equal to m naught sine omega t. So these are what's happening along the x and y axis. So how does the signal take place? So the X is going to be proportional to mx, and Sy is going to be proportional to my. We do not know the exact magnitude, as it is not that important. So what we do is we can write it down as S of t is equal to Sx plus Isy, which is then, I can call it as m naught times cos omega t plus iota sine omega t multiplied by e to the power minus t over t2. So this is how your FID is going to look. This envelope being minus t over t2, and this area being this magnetization along x and y. So R is equal to 1 over t2, which is the rate of decay of this FID. So there was another tau explained earlier, like that tau is 3-cycle decay. Tau can also be 1 over t2, but here I would stick to R as being 1 over t2. Now the next step is, how do you visualize the signal? Like once you know that, okay, you've got the signal, then you're going to Fourier transform it. So how does the Fourier transform work? S of t, when you Fourier transform it, you get it into S of omega, which is like from going in the time domain to the frequency domain. So what formula does it follow? S of omega Fourier transform your NMR signal, you are going to get another equation in the form of omega, which will be your resonant frequency, or the frequency at which you will see the peak. So at that time, like I wouldn't go into how the equations look like. You can Google it because it's outside the scope of this lecture or lab. So it will be of the form A omega So this is called as absorption spectrum, and this is called as dispersion. And briefly I'll tell you how these look like. Just here. A of omega and B of omega absorption and dispersion, and this peak will be centered at this omega, the offset frequency, and this is going to be 1 over R. So this is how you go from a signal collecting FID into how you go into the spectrum.
Okay, so now we're going to start experiment 2. We're going to do the spin echo sequence and use that to measure T2. So in the first experiment, what we basically did was approximate the 90-degree pulse, but it's difficult to get that exactly right without first finding the 180-degree pulse. So what we're actually going to do first is to optimize the 180-degree pulse. So if a 90-degree pulse brings all of your magnetization from Z into the XY plane, then that should receive maximum signal. A 180-degree pulse brings all your magnetization from Z to negative Z. Signal cannot be detected if it's in Z, so that means what we're looking for is a minimum for no signal at all. And it turns out that it's actually easier to see where there's no signal than where there is maximum signal. So what we're going to do is find that 180-degree pulse. Okay, so we're leaving everything else the same from what we did with experiment 1. So this P, the period between our pulses, is still 5 seconds. The frequency here is still 21 megahertz. And now what we're going to do, we estimated the 90-degree pulse to be about 7.2 microseconds from experiment 1. So if that's about 90, then about 180 should be 14.4. So I'm going to increase the length of the pulse all the way up to there and see what happens. And we can see along the way, our signal is decreasing. So when I'm at 12, it's less signal. When I'm at 13.08, that's much less signal. As we get closer, we'll see a lot of very close to 0 or approximately 0. So I'm going to about 14.4 is what I said, because we had 7.2. So if we can zoom in to that spot. So we can see just that there's no signal here except for this one sharp thing that's always there. And I can keep trying to optimize the signal. And it turns out that we get close to 0 at about 14.8. So we can see the difference. When I approximated it, it was 14.4. So that's that. And then it turns out there's actually less signal if I go to 14.8. So that's there. So actually our 180-degree pulse is 14.8, and our 90-degree pulse is actually about 7.4. So that's good because it's close to what we had guessed, but not exact. So now we know for sure. Okay. So now to perform the spin echo experiment, we're going to first apply the 90-degree pulse that we now know is 7.4 microseconds. Then wait a period of time tau, then apply the 180 degree pulse, that's 14.8 microseconds, and then detect and repeat that experiment. So that's what I'm going to set up by changing the length of A, that's our first pulse, is to 90 degrees, which is 7.4 microseconds. And we'll see our big signal again. Okay. Now B is the length of our second pulse, that's a 180 degree pulse, and that's going to be 14.8 microseconds. Now with the tau, the period between the pulses, we're setting to 10 milliseconds. So that's 0.01 seconds. The number of B pulses, 180 degree pulses we're going to apply is 1. And then the time in between experiments, we're going to put that to 10 seconds. And then turn the B pulse on with this switch. And so we initially got stuck here. We didn't see the echo shape. So we should see the 90 degree come down. And then we should see what we see here at tau. There's that little glitch in the middle. And then from the same distance, from the 90 degree signal to tau, there should be like a hump, which indicates the echo. What I think the issue was is that our magnet is not actually tuned properly to hydrogen, which would be 21 megahertz. Instead, we found that the resonant frequency for hydrogen on this instrument is actually about 21.062. So I'm going to change the frequency to that. 21.062. And now we have exactly what we expect. So the 90 comes down, we have a glitch there at tau. Like it says, if our 180 degree pulse was perfect, the blip at tau would not appear. But you want to minimize that blip as much as you can, so that's what we've done. It's very unlikely on like such a inefficient instrument such as this to get perfect pulses. It's pretty much impossible, but we can get pretty close, and that's what we've done. So then again, for the same distance tau from the 90 degrees to the glitch, we have the 180 degree echo. So this whole thing from the first pulse to the last, or from the first signal to the last signal, is 2 tau. So now what we're going to do is change the delay time, and we're going to measure the amplitude of that echo signal. So you should do that.
I think real quick, we might want to go through and just average at least a couple.
Okay.
So we can get just a better idea of what our baseline is. Let's actually keep this down to 2 averages, just so that we're not waiting a minute between every single change of parameters. Okay.
So remember that for the spin echo experiment, we're actually plotting using 2 tau. So our first tau is 10 milliseconds. So our first data point should be 2 tau, which is 20 milliseconds, and that'll be on your x-axis, and on your y-axis is the what we're going to measure using the scope, the amplitude of that signal. So it should be 20 milliseconds on x, and y is,
let's see, our amplitude is 2.15 volts.
okay. So now we're going to go from 20 milliseconds to 200 milliseconds. So I think if we go that high, I found that we don't actually get signals, so I'm just gonna, let's just see what happens, I guess. So let's go to 11, so that's actually 22, 2 tau. And the amplitude is?
Right now, 2.20 is going up.
And then if we go to 12, so that's 24.
Seems pretty unchanged.
Yeah, so the first few points will be about the same. Let's go to 15, which is 30.
And
About
still
the same.
Yeah.
Okay, let's go to 20. So that would be 40.
Right. So this will update every 20 seconds.
No, this is tau. Oh wait. Oh, I am changing the wrong thing. See, this is why it's important to pay attention to what you're doing. So the period should be 10 seconds. Okay, so what we're changing is the tau. That's the period between these. So, okay, yeah, so our first one is...
Roughly 2.20 volts.
Yeah, so that's 10 milliseconds. So that's actually 2 tau would be 20 milliseconds. That's what you're plotting. Okay, sorry. And I'm gonna go.
See, even the grad students make mistakes sometimes.
Yeah.
We're all human.
Some of us make a lot more mistakes than others.
Yeah, I bet.
So then we have 10.5 milliseconds.
And that's 1.23 volts.
Okay.
Ooh, hold on. Maybe we should wait for that to
Oh yeah,
stabilize a
because
little bit.
it's
Yeah,
averaging.
It's averaging the
Okay,
previous two
so I'm
pulses.
gonna leave it at 10.5.
Yeah, let's. Yeah, because we should wait about 30 seconds,
Okay.
right? About 3 periods, we should be fine. Yeah, and then we shouldn't see as much splitting anymore once this is averaged correctly. So now that puts us at 2.08 volts for 2 tau is equal to 21.
Yep. Okay, sounds good.
It is 2.08 volts.
Okay, now I'm gonna go to 11 milliseconds and wait for that signal to average.
Yeah, so you'll see it split half first, and then the next time it updates. And that first peak is at 1/4, so. What's the rule of thumb? 5 half-lives, right?
Mhm. Okay.
Cool. We're at about 2.14 volts. Odd that we went up, no?
Yeah, but the first few will be about the same. I'm gonna go to 15 milliseconds, so 2 tau is 30. And also, yeah, the signal's gonna get further away because we're increasing tau.
Yeah, so we're just gonna shift on the time axis, just the offset. Okay, that's a little bit easier to see now. So 2.10 volts.
And I'm gonna turn.
About a 2% change. That's
So it's about 0.017, so that's 17 milliseconds, so 30, 2 tau. 34, 2 tau.
yeah. Okay, and that looks like it is at 2.04 volts. I'm going to change the time scale. I'm going to make this a little bit longer. Here, on the way.
How many points do we have so far? Like 3, 4. Huh?
5.
Okay. So I'm gonna go to 18, So 2 tau would be 36.
We're at 1.97 volts.
And I'm going to go up to 20, so 2 tau is 40 milliseconds.
Here, that's going to be huge. So move this over. Take a couple cycles. There we go. 1.88 volts.
21 milliseconds, so 42 2 tau. And we're just getting a bunch of data points. It says about 10 to 20, but we'll take a bunch until we see no signal at the end, basically, I think.
That's a good idea.
Yeah.
Let's see. Okay. 1.68 volts.
So let's go to 22.5 milliseconds. So 45 2 tau.
Okay, that seems to have averaged out now. 1.64 volts.
Let's go to 25 milliseconds. So 2 tau is 50.
Isn't the anticipation killing me? Okay, that looks like 2 cycles have averaged. That's at 1.55 volts.
And let's go to 30 milliseconds, so 2 tau is 60. If it decreases too fast, we can like go to points in between, I think. Like, yeah, this one might be a pretty big decrease. And maybe not.
Yeah, because we have to wait for
Yeah,
several averages.
yeah.
Once we see that original peak go away, we'll know it's averaged out fine. So probably needs one more period, it looks like. And that looks like 1.28 volts.
And let's go to 35 milliseconds. 35 milliseconds. So 2 tau is 70.
at 0.97 volts.
And let's go to 40. Let's go to 37.5 milliseconds. So 2 tau is 75.
Have to change the offset a little bit. More period. Okay. And that's reading 0.81 volts.
And we'll go up to 40 milliseconds, so 2 tau is 80.
Probably needs one more average, it looks like. Previous peak is still diminishing. We'll give it one more period. See if it doesn't move. Oh, that looks good. So that's 0.69 volts. So it's settled at.
And we'll go to 42.5 milliseconds for tau.
Probably bring the scale back a little too.
So 2 tau is 85. And we're seeing that, as I explained at the beginning, as we increase the tau, the signal we get goes down. And that will allow us to extract T2. Although I've noticed in the lab manual it doesn't actually really talk about that. But you do have to report it in the lab report, so maybe at the end I can go over that again.
Okay, this data point reads 0.56 volts.
I'm gonna turn tau to 45 milliseconds, so 2 tau is 90.
Okay, that seems like it's caught up. Maybe I'll give it one more period just to make sure. All right, settled at 0.46 volts.
Let's go to 47.5 milliseconds for tau.
Yeah, I bet you I could make this faster if I switch this back to sample mode when it triggers once.
Okay.
And then allow it to re-average so that we don't have to wait 3 or 4 periods in between. We'll wait for the next trigger to hit and we'll make sure that that didn't change. Okay, that looks good. So that's going to be 0.41 volts.
Can you just zoom in on this part? Because that's the only part we have to see.
Yeah, here. Let's change our scaling.
Yeah.
So, yeah. Move this up here. Let's change our baseline. So here, if we're going to be a little bit more accurate, can we change that last data point to 0.388 volts? Oh, it's going even more down. What's that?
I didn't change anything.
Here, actually, let's, I'm sorry. I was too hasteful. Too hasty. I don't think hasteful is a word. I think it's fluctuating a little now. Yeah, I'm impatient. That's actually that's...
What did you set it to like average?
It's only averaging 2 points though, so
I don't know.
Right? It shouldn't be flipping around that much.
It shouldn't. I don't know.
All right. Well, if it doesn't, all right, it's not moving at that one. Oh, fuck it. This is probably just fluctuation and noise, I think.
Yeah.
So let's rate that out at 0.384. I guess if we increase the number of samples that we average, we'd get less of this fluctuation.
Yeah.
But then it would be roughly like a minute and a half per.
Yeah.
So
yeah.
Maybe we don't want to do that.
Yeah. Okay. So I'm gonna set tau to 50. So now we're at 2 tau is 100 milliseconds. And it said in the manual to go up to 200 milliseconds, but we're already pretty close to. We're already at very low signal, so I'm probably not going to go for too many more points. But we'll get a point where there's almost none.
We're going to rate that as 0.336 volts. 0.336 volts.
Okay, I'm going to go to 55. So 2 tau is 110.
We'll probably end up somewhere around right here. Here again, what if I quickly just acquire a single sample so that it comes in with the next trigger. It'll read just one, and then we'll average. So next thing that comes in should look fine. Okay. That reads 0.212 volts.
And let's set tau to 60. So 2 tau is 120.
Alright, now it's triggered. I'll go back to average. Just save us, a few 30 seconds maybe. Alright, that reads 0.128 volts. Might fluctuate by like another 5 volts.
I'm going to set tau to 65, so 2 tau is 120. We're pretty much almost at no signal. But we can still see a little bit, so we're going to keep going.
Scale down. Come on.
I think it's going to be pretty much no signal.
Right.
Yeah.
Oh, let's just give it one more trigger to
Yeah.
be certain. But yeah, anything less than 100 millivolts is pretty much noise on this oscilloscope. So 0.082 volts is what we're going to read out last point, and I think that's as close as we're
Okay.
going to be able to get.
Then that's the end of experiment 2.
Yay! Echo we want to see, right?
Okay, so we just did the spin echo experiment in order to measure T2, and now we're going to do the inversion recovery experiment in order to measure T1. So in the inversion recovery experiment, we start with the 180 degree pulse. That brings our magnetization down to -Z. Then we wait a certain amount of time tau, and that just decreases the magnetization along -Z. Then we apply the 90 degree pulse and measure that magnetization. So really what we're measuring is that magnetization along -Z after a certain amount of time tau. And as we adjust tau, we can see that, well, first we're applying the 180. If we have a very short tau, then the relaxation won't have a lot of time to take place. So then after the 90, we'll have a lot of signal. And when I showed you the chart on the board, and when you do this on the lab report, we consider that the negative Z signal, so that's why we start in the negative. As we increase tau, the magnetization along -Z will increase, and thus the final magnetization you measure after that final 90 degree pulse will also decrease, and eventually it'll go to 0, and that'll be our tau null. And that's usually what we use to estimate T1. And then as we increase tau further and further, we're allowing the magnetization to not just go through 0, but then go back up to positive Z. So when we apply that final 90 degree pulse, it's just like we're doing a pulse acquire. Eventually it'll be our maximum signal. Okay. So in order to set this up, we start with our 180 degree. So I'm going to change the length of our first pulse to 180, which was about 14.8 microseconds. And then we're going to change the length of our second pulse to our 90 degree pulse, so 7.4 microseconds. Okay. Tau we're going to put at 20 microseconds to start with for this. And then the number of B pulses is still 1. Our period is still 10 seconds. We're keeping our B pulse on, but now we're turning the sync to B. So the scope only shows the signal after the B pulse, the 90 degree pulse. And so now we see it's this signal in the middle. That's after our 90 degree pulse, and we're measuring the amplitude of that. So just remember that as we approach 0, we're considering those values negative. Around 0, we're not sure whether they're going to be positive or negative, so you can leave some of those points out. But you want to get like a good estimate for tau null. And then as we go past 0, and we're going to go way past like into seconds, probably up to at least 5 seconds, we're going to see a large signal. So we start with our tau at 20 milliseconds. And this is not 2 tau, we just have the 1 tau. So in version recovery, we're just doing the intensity of the signal against the tau time on the x-axis. Just 1 tau. So yeah. So at 20 milliseconds, the amplitude is
reading currently 1.93 volts.
And we're going to be doing a lot of these points because they can be a little strange. But then we'll see at some point the points will get, it'll be hard to differentiate between them. We're going to have a lot around the null, but then we'll see the signal go back up again. So let's go to 30 milliseconds.
And that looks like 1.88 volts.
And 40 milliseconds.
Okay, and after this we'll probably change our time base. Currently it reads 1.83 volts at the amplitude.
And 50 milliseconds.
Okay, here let me change the time base because we don't have enough time there. Let's wait for this to trigger a couple times to actually bring in our signal. Okay, so we're currently at 1.82 volts.
And 60 milliseconds.
Gonna have to wait a full 10 seconds to trigger. There's gonna be a lot of waiting for for data to arrive to the oscilloscope throughout this part of the experiment.
And then when our taus are so long, they're in the second time frame. That adds even more time because now we're just at milliseconds. So
Right. Okay, let's wait for this to trigger one more time, and it did. What is that? That reads 1.81 volts.
70 milliseconds.
Okay, let's wait for this to trigger again. Excellent, that's at 1.80 volts. Okay. Here, I'm gonna also increase the time base again.
80 milliseconds.
Yep. Okay. Let's give it one more trigger just to make sure. .79 volts.
90 milliseconds.
As we get closer and closer to D0, right, we should see more drastic change in amplitude. All right, we're currently at 1.75 volts.
And 100 milliseconds.
Well, let's let that trigger one more time just to be sure. Okay. And we're currently at 1.69 volts.
Okay. I'm gonna go to 200 milliseconds. So
Oh, here, let me change the time base one more time. So now we're at 100 milliseconds per division. And I'll let that trigger one more time before I record. All right, that's 1.51 volts.
300 milliseconds.
Back up another trigger. If not, we might want to start averaging. Yeah, I don't want to start averaging because it's kind of bouncing around.
Okay.
So we're going to go just to average previous two, just so we can get rid of some of this random noise. right, that seems pretty stable now. That's 1.16 volts.
Yeah, 400 milliseconds.
Oh, here, let me do that little trick of go back in the live feed for a trigger and then let it average afterwards, so that we're not trying to average out malarkey. Yeah, so this reads 1.17 volts. So in general, it should probably be decreasing, but we'll have some noise in the voltage amplitude, so
It's
it'll
just weird.
yeah, it'll bounce around.
And it's 500 milliseconds.
Okay, here, just so we get this all in the same time interval. Seems to be a little happier. Let's go back to simple. Wait our 10 seconds to trigger. Go back and average. We'll want to trigger twice, trigger once. And a second trigger. Puts us at 0.880 volts.
600 milliseconds.
So let's wait for the trigger to come in. Boom. Let's average. Averaging will become a lot more important the closer and closer we get to zero. I'll give it one more trigger. That seemed to have bounced around just a little too much. Okay, seems pretty stable. 500 millivolts, so 0.500 volts.
– 700 milliseconds.
Okay, increase the time base one more time. Exit that out, the trigger to come in. Excellent. Now let's average. Okay, so it's currently at 0.710.
To do 800 milliseconds. I think as we approach the null, I'm going to do some additional points as well. So maybe next I'll do 850.
Let's average out. Let's wait for one more trigger to average. We're at 0.570.
I'm going to go to 850 milliseconds.
I think you might benefit from changing the voltage scale a little now. So it means you're going to want to change this, you're going to want to change this. Probably go back to a single acquisition really quick. So it looks like 0.208.
900 microseconds.
Sorry. Let's do a live acquisition just so it throws away the data we don't need. Alrighty, now let's average 2 of these so that we can deal with the voltage fluctuation. Some of them might have to do with like the crosstalk of leaning on each other. Also, if you end up shaking these a little bit. All right, maybe just one more trigger. So that's where it is. 0.164.
950 milliseconds. For the subsequent experiments where we're going to be doing the same experiment on different concentrations of copper solutions. All we're going to be doing for those is looking for just the tau null. So we don't have to, we're going to be doing this basically, but just very quickly and not recording every single point, but just seeing where there's no signal after the 90. So we can estimate the T1 from that. Whereas this, we want to see the whole thing and get a lot of points so we can more accurately determine the tau null.
So that is reading 0.158 volts.
Okay, and now 1 second.
Increase the time base. All right. Let's average. Average one more time. Okay. 0.144 volts.
Okay, that's 1.1 seconds.
live acquisition for instruments averaging. I don't see anything. I think that's because we're approximately at null.
Yeah, this might be the tau null about here.
That's what it looks like to me.
Okay.
We'll let it trigger one more time just to see if something pops up.
Okay.
Nope, looks like we're sitting at tau null. So we'll read about 0 volts.
So the reason tau null is important, like I said before, is that tau null allows us to estimate T1. So tau null times about 1.44 will give you the T1. And then T1 times 5 is about the time you should wait on your delay between experiments. So our delay here is 10 seconds. So that's well over. But it's probably better to be over than under. It just takes more time. But also you want to be able to know about what you should be at, because you don't want to go way over. If you have really quick relaxation, then you should have shorter delays. You don't want to be wasting time with your experiments, but then also you don't want to assume that you have a really quick relaxation when it's actually very long and you need to set your delay longer. So that's why this is important for me in real life. Okay, so, and a lot of these will probably be about the null, so, but we should see it go back up, but we might have to, I'll probably go in increments of 0.1 to 1.5, and then maybe jump it up to 2 and see what happens. So I'll go to 1.2 seconds.
So, I don't know if this little peak right here is what we're seeing. We're still probably so close to tau null that we're below the signal to noise on this equipment. So, probably read this as 0 as well.
Okay. Let's go to 1.3 seconds.
Yeah, I don't know if you want to count that little noise blip here.
No,
So,
we'll call that 0 too.
yeah.
It's 1.4 seconds.
Yeah, so we're still pretty below the noise. I guess if we averaged like, 32 scans, but then that's 32 seconds
Yeah, we
every
don't
time we're
wanna
looking
do
at. We'll see more drastic change.
Yeah. So this is 1.5 seconds.
That's also zero.
Yeah, so I mean it's effectively zero. It's below the signal to noise. We can't really discern it from the baseline right now. I guess if we averaged it a lot, we'd be able to, but
So we're waiting for this to go to zero.
well, we already went past zero, so we should.
Yeah, we're
see
waiting for it to go back up.
Yeah, but I think just like the amplitude is so small relative to
Yeah.
the noise we're seeing in the baseline, we're just not seeing anything discernible until we get way later in time. We'll see it pop up. If not, we could always go back and average 32 times every time. So I wonder if we're going into like a little bit of a jitter problem right now. So we should see that first part. I don't see anything. See if we can find our pulse again. Do you remember that patience is a virtue? I don't even see. There's the original pulse. Okay. Yeah. Wow. I've seen nothing. So look, even if we average like 16 of these, we just see the baseline settle down quite a lot. But then that's what 160 seconds. So
Okay. I'm just gonna go put tau to 2 seconds.
okay. Here, let me pull this down and go back to sample.
Okay.
We should definitely be seeing something. Yeah, this should be something great. This is our initial pulse, 2 measures away. We're at 1 second at division, so... there we go. Okay. So, let's go back and average. So, we first hit 0 about like 1.1 to 2.
So why do you think the signal comes and goes? Like it just
Oh,
did?
yeah. So I think this is an issue in the scope. I mean, not that the scope is necessarily broken, but this is a common noise problem you get with oscilloscopes, right? Like, so you can get jitter in both time and in voltage. Really expensive high-end oscilloscopes have really, really, really small jitter. The jitter should actually be decent on this oscilloscope, but since we're really small voltage amplitudes, right? We're at like 100 millivolts, which is not much. If we like go down here and we actually look at the amplitude of our bandwidth, it's about 56 millivolts. So if we jitter by even like 20% in the voltage dimension, we're losing an appreciable amount of our signal.
Mhm.
So this is also something that if you sit here and you average enough, this effect goes away.
Mhm.
So let's just, for humor, let's average 4 times, and you should see it jittering less.
Mhm.
What's also strange is that, usually jitter is a bigger problem at shorter time intervals than it is longer. But again, a lot of that's going to be really equipment specific.
Mhm.
So that's our first pulse. It's our second for average.
I think even if these measurements, like after the 0, aren't super accurate, we at least know that we passed the
Yep.
null time, because even at those times around the null, we were just never seeing signal.
Right,
Whether it was
right.
like the jittering or just straight up lost in the noise, we weren't seeing anything at all. But now we're getting some signal sometimes, so at least we know we're past that point, and we can sort of figure out some way to make our data look good, I think,
Yeah.
based on that.
So you see it after averaging it 4 times, it's pretty stable. It's not like
Okay.
completely disappeared.
Yeah, that's good.
Right? So if it's missing like 1 out of every 4 pulses, right? Even though if everything's set up in the trigger properly, we should never miss a pulse. But okay, let's read this out at 0.14 volts.
Okay, let's go to 2.5 seconds.
Here, let me turn the averaging off while it catches up to that.
And eventually we're going to reach a maximum amount of signal, because that will indicate that the signal has totally relaxed back to Z. And then, like I said, that final 90 is basically just a pulse acquire. So it could be as we get to higher and higher times, we're going to see the same amplitude on that final signal, or very close.
Oops, I do not want to average 140 times. I want to move the cursor. God, could you imagine 256 times 10? Data point? Oh. It's the price you pay for good signal to noise. What an average it's for.
I hope our experiments aren't perceived as dull. I don't want to have the dullest experiment, Like I want to, when the students talk to each other, while behaving in a socially distant way, I want them to say like, "Wow, that NMR experiment and that GC experiment, those were really interesting." But those other ones, man, they were dull.
You know what's funny is I'm getting negative amplitude now.
Okay.
But I know that's a fixation with the noise. I can fix this. Honestly, if we look at this in like a 2 pulse envelope, so it's just like a moving boxcar of every 2 scans, it'd be a little easier to catch. Oh man, just wait till gas kinetics and we get to watch a bag full of air.
That sounds exciting.
It is exciting. Let's talk about air pollution. I love that.
I think all these experiments are 2 hours of looking at a computer screen.
Yeah. Well, I mean, like, it takes 10 minutes every scan of GC, and that there's like, for like a good set of data, there's like, what, 25 scans? So, well.
That's science sometimes. I mean, my entire job is looking at a computer.
Yeah.
I just sit there. I can do it from home. I just sit on my computer at home.
Got that work from home life, right?
Yeah.
Here, I don't think it likes this very much. Let me just see if this stops freaking out. Eventually we'll hit high enough amplitude so that I won't have to be so zoomed in.
Right.
And it's a little bit better too. In fact, why don't I just drop that now, because I know that we're at least better than previous. Okay, this seems to be pretty stable now. Maybe not. Alright, let's give one more trigger. God, yeah, the last set of experiments I was running before, we had the whole shutdown, we can't go back to lab. It was like, I had to run 120 different scans at 12 minutes each. Like one single shot of experiments.
Well, NMR experiments are like 16,000 scans at like 2 seconds each. Usually.
Oh, goodness. That's the price we pay for progress, right? Hundreds and hundreds of man hours just waiting on the collection. And that's technically the fast and easy part too. Okay, there we go. We're a little bit better now. So seem to have caught back up. We're gonna read this out as 0.716 volts. Not 7 volts.
Yeah.
That would destroy this oscilloscope.
Yeah, let's go up to 3 seconds. And I think when we see the negative amplitudes, that's really just like the start of the pulse.
I think so.
That's sort of what it looks like.
Right, because you've got that dip down.
And then just like, yeah, the rest of it is lost wherever in noise or whatever.
Yeah. I was having an issue with this in one of the scopes in my lab. We actually had to get aluminum foil and wrap it around the BNCs on top of it. Get some extra shielding. Worked like a charm.
What we have to do sometimes is like lift a wire up and hold it there as you adjust something else.
Yeah. Well, you'd be surprised the amount of crosstalk that happens on, like these data that you're transferring via RF. Do you think any of our students remember the days of cable?
I think so. I mean, I remember it, and they're only 5 years younger than me.
Okay.
Well,
yeah.
5 years is a long time.
Yeah. Right. Let's assume you're about 5 at the time you can have long-term memory, right? So, what's the earliest memory you have of cable?
Watching like Nickelodeon.
How's it going? Yeah. It's long pulse time, so it takes quite a long time to catch up.
I don't play $20. Okay. All right, what's going on? Can you guys finish?
Yeah, I think so.
Yep, that's the idea.
Okay.
Okay, it seems to have caught up.
This is
And just as I said that, it went away.
Yeah.
Well, it
We can
just
wait for
went
it
away
again.
as I said that. It'll come back in the next trigger. Please come back in the next trigger, I hope.
I feel like
How about
the thing with cable and the thing we don't have anymore is like you would be channel surfing and you'd like start watching a movie like in the middle. Like we don't do that like my parents maybe because they're old.
Right.
Like, we don't do that. That's insane.
God, there were so many like classic films that I had only ever seen the first
you
or the
know,
last half
yeah,
of.
exactly. So many movies like, and now it's like, I'll be watching a movie and be like, have I seen just these 10 minutes before? Like, why is this so familiar?
And yet I know nothing about the plot.
Yeah,
I don't get
like-
it. Do you have like one of those? I mean, I guess this was pretty much done by the time we were kids, but like, yeah, you remember the antennae?
I didn't have
People-
any antenna.
I had really old TVs growing up. God, those were obnoxious, and that's just the whole issue. Is just electromagnetic noise. BNCs they're better than some alternatives, but they're not perfect. And I bet you if I can keep all these wires from touching,
Yeah.
I'm sorry, viewers at home. See? Now if they don't touch, you can read out. Now if I just screw a third arm, I could also adjust this. Well, such is life,
I
right?
think next time we see signal, just take it.
Yeah, I think that's what I'm gonna just do.
And then I think we're only going to go to 5 seconds in steps of 0.5, so this won't take too much longer.
So that reads like 0.196 volts at the 3-second mark. 0.196 volts for 3 seconds on tau.
Let's go to 3.5.
I might need to increase the time base even more. Which can also be an issue because you're compressing the signal. Make it a little less discernible from the baseline. Come on. Please work. I'll catch up to the next trigger. Hey, that's a lot of signal, but not in the right places, I think. Oh no, some of that is in the right place. But now that the time frame of the scope, the time base is so large, we can see the next set of pulses coming in.
Mm-hmm.
So let's hit this trigger one more time. Hopefully it doesn't go away. It's caught up. If not, I remember what this amplitude is. Seems a little low. It's not gone on the next pulse. We'll write it down. Should have knocked on wood. Remind me, tau is the separation between pulse, right?
Yeah.
So part of why we're losing signal might be, well, no, because even at 2 tau is still less than the period at this point, right?
Yeah.
So I know once 2 tau is about the period length or larger, we'll just get nonsense back at the oscilloscope.
Well, not really with this experiment. Because...
Oh, that will affect the relaxation, yeah.
Yeah, because this is just like, if we make tau insanely long, that last pulse is just like 90 degrees acquire.
I see.
Which is just the first experiment.
Yeah. Okay.
I think it's just
fluctuating at this point from some
Yeah.
noisy cables, but I was able to get that last amplitude reading. That was 0.180 volts,
That's from 3.5.
and that's, yeah, for 3.5 seconds.
So let's go to 4.
triggered middle of changing parameters, so it's still kind of freaking out.
Even if we don't get anything up here, we have a good sense of about the tau null.
Right.
And some positive points, so they can put a graph on the lab report. But let's keep going until we get to 5 seconds.
Yeah, here, I'll let it trigger one more time and I'll write down whatever amplitude it
Yeah.
is. So long as it's, not zero,
Yeah.
ideally. Triggering. Okay, sweet. Here we are at 0.472.
So this does make sense because it's the first pulse, then 4 seconds of tau
Yep.
to there, and then the 10 seconds. That's only 5.
Well, it's 2 per
6.
division.
Yeah, so the distance from here to here is 2, 4, 6.
Oh, yeah.
But our period should be 10.
Right.
Interesting. Why 6?
So there's actually in trigger protocol, there's actually a lot of like tugging that can happen between pulses. So like, you're going to do like transistor logic. So when 2 pulses are nearby each other, they can drag each other towards time.
Okay. So actually, the period is from the first pulse to the next first pulse, not from the last pulse to the first pulse of the next cycle. So this is actually, so that does make sense. It's 4 seconds plus the next
Plus
6.
6.
So that's a total of, that's your total period of 10 seconds.
Right.
I think that makes sense.
Yeah, I believe it.
Okay. 4.5 seconds.
Yeah. Once this gets closer and closer to like hitting when 2 tau gets close to P, you'll see that the next pulse that comes in drag towards each other a little. But in our time base, we shouldn't see it because it should be tugging like milliseconds or less towards each other. Really, if it's really good trigger protocol, it's like they'll tug each other by tens to hundreds of nanoseconds. But yeah. So delay generators cost a lot of money. Let's trigger, come on. Excellent. Should be considerably less than what we got before,
It's okay.
but it's reading out at 0.288 volts.
At 4.5.
Yep. And now let's go to 5 seconds. That'll be our last one.
Yep. Now, ideally it shouldn't freak out, but it just might. So if you are actually here in the lab, this would be a great downtime to be, calculating.
Working on your lab report.
Yeah, work on your lab report. Figure out what you're going to do for your serial dilutions or your copper solution. Work up the data from part 1. Make the most out of this. That seems pretty small for what we should be seeing, but I actually also don't believe that this is fully caught up because the first pulse isn't in here yet. Okay, so I can see the first pulse, and that looks believable to me. That's sitting here at like 0.24 volts.
And I think that's it for experiment 3.
Guess it shoots back up a lot.
Okay. Okay, so in order to do experiment 4, we are going to use 4 different solutions of copper ion and water. So the first it gives you the instructions for, and then the other so that first one is going to have a concentration of 0.00125 molar. Then we're going to be doing higher concentration solutions of 0.0025 molar, 0.00375 molar, and 0.005 molar. So I'm going to show you how you would make each solution. So the first thing is we're going to measure 40 milliliters of millipore water in our graduated cylinder. That's 40 milliliters, and we don't have any good markers, so I'm just gonna have to remember which beaker is which. Unless, oh, good. Found a Sharpie. So I'm going to label each beaker ahead of time for which solution I'm gonna use. So this is 0.00125 molar. This is 0.025 molar. This is 0.00375 molar. And the last one is 0.005 molar. So 40 milliliters of water. Then 50 microliters of the 1 molar copper solution into the water. So to measure 50 microliters, we use the pipetter. This pipetter is from 10 to 100 microliters. So if we set it to 50, where the line is like the decimal place, this indicates 50 microliters. And going to use the pipette tip. And then put that into our beaker. When you use the pipette tip, we like to mix by just making sure we get all the solution that we want to go in there and push it in and out. So that's a little bit of mixing. And then we don't want to use this for another solution because it touched the water, so we just get rid of the pipette tip somewhere. Okay, and okay, so I'm just going to make all the solutions first, and then we'll transfer them to our NMR tubes. So I'm just going to mix a little bit more by swirling, but it should be pretty easy. Excellent. Now for the next solution, we're again going to get 40 milliliters of molten water. So that's 40 milliliters into this beaker. And this is the 0.0025 molar. This time we're going to add 0.01 milliliters, or that's just 100 microliters. So I'm just gonna not even change this. I'm just gonna do 250 microliters. And because I'm going to put the pipette tip back in the same bottle, I'm just going to make sure it doesn't touch anything. And then use it to mix again. Okay, get rid of that. And again for the next solution. 40 milliliters of water. That's 40 milliliters in here. And the next amount of the 1 molar proper solution to add is 0.15 milliliters. So that's 50 microliters times 3. So I'm just going to do that 3 times. Mix. And then the final solution. 2 milliliters, so that's 4 50 microliter additions. And cap this. Use this. Throw the tip away. And we made all 4 solutions, so now we can go back to the magnet and finish experiment 4. So I put in 100 microliters of the first solution. So that's the 0.00125 molar solution into this NMR tube. So now I'm going to change the sample. This is pure water, and I'm putting in our first solution. So this is the same experiment, the same inversion recovery experiment, but now we're going to show that the T1 times decrease with when we're adding in these ions, in this case the copper ion. That also means our T null will go down as we are adding in more solutions. So this is the lowest concentration of the ion, so it should be less than the tau null of the pure water that we saw. That was about 1 second or so. And we're going to see where the tau null is for this solution. So to do that, we don't have to do every point that we did for the last experiment. Instead, I'm just going to go through quickly. I don't have to record anything except for when I think I have tau null. So I'm just going to show how to do that. So we can see I set my tau back to 20 milliseconds, and we can see that our 180 and then our 90 here I put in the middle. And so again, we expect it to start at a large amplitude. It'll go through 0 and then go back up. But all I want to record is the tau I'm at when it's at no signal there in the middle. So I'm going to start increasing the tau. So starting at 20 milliseconds, I'm going to first increase it to 50 milliseconds. And I'm just going to keep track of it. We can see that it went down a little bit. And I'm just going to ignore the first pulse, because all we want is the amplitude of this. So I'm just going to keep this in the middle and keep track of that. Okay. So we're still pretty high, so now I'm going to go to 100 milliseconds. Okay. Okay, I can keep going up pretty quickly, so now to 200 milliseconds. Okay, so that went down a pretty decent amount, so now I'm going to take smaller steps of tau. So now I'll go to 210. $220. $230. I'm also going to increase the scale just so I can get a good sense of when it reaches the minimum. 240. Let's just go to 250. Okay, we're getting closer. 270. Okay. 280. Increase the scale again. Okay, that was too much. 290. We're getting very close. .300 milliseconds. .310 milliseconds. .320 milliseconds. We're almost there, so that we shouldn't be able to see the maximum point when we're at tau null. Should be lost in the noise. Whoops. 330 milliseconds. So I think we're there at 330 milliseconds. So I'm going to call that tau null for that first solution, 0.00125 molar. And now I'm just going to increase the tau back up so we can make sure that the maximum is after this point. 330 milliseconds. Milliseconds. So we can already see it went back up a little bit, so that's good news. So let's go to 400 milliseconds. And went up a lot. So that tells me that, yeah, our tau null is about 330 milliseconds. And if we keep increasing, that signal will go back up, and that's the top of our T1 curve there. But all we care about for these experiments are getting a tau null, which we got. So that's the end of the first solution, and we can just leave it filming, and I can do the other ones right after. So I'm going to put everything back in preparation for the second solution, keeping in mind that our second solution will have a higher concentration of ions, so its tau null should be smaller than 330. So I'll be careful to keep that in mind, and I'm just going to put everything back to normal, put tau back to 20 milliseconds, make the scale so that I can see everything. Okay. And now I'm going to get the second solution. So this is the 0.0025 molar solution, and I'm going to cap it. Okay, and I'm going to change samples. So we can see again that signal in the middle, and again I'm just going to go through and increase the tau time. It should hopefully be less than 330 milliseconds. So first I'm at 20. And I'm going to go to 30. That's a little less. I'm gonna go up to 50. Still only a little less. Let's go to 70. Let's go to 100. To 120. $150. Let's go to 170. Let's go to 200. $220. $250. $270. $300. $320. $400. So it should have been less than 330, but it's not. But that's what we got. $420. $450. $460. Let's go to 500. $520. $550. $570. $590. $600. 10. It's pretty close to the null. So I'll call it there, about 620 for 0.0025 molar. Let's see what happens with the other solutions, because maybe they're, I don't know. Because it should have been less than the first one, but that's okay. So let's see if we can go back up to 650 and that signal should increase back up again. Let's go to 750. So it's increasing back up a little bit, 800. So we can see it increasing back up. Let's go to 1 second. So again, increasing as we increase tau. So let's move on to the third solution. And let's put this tau back to 20 milliseconds. So this is the third solution, 0.00375 molar copper ion. And I'm gonna cap it. Samples again. Okay, so again, we're going to start at 20 milliseconds and slowly increase. So let's go to 50. Now let's go to 80. Now let's go to 100. $150. $200. $250. $300. 350. $400. $450. So we're getting pretty close now. $470. $500. $530. $550. $570. $600. So I think I went through the null already, so let's try about 680. Okay. 670. $660. Try 665. So I think that's about as close as we're gonna get, so let's actually do 665. We're zoomed in a lot, so just a little bit. So yeah, let's call that town null 665. And put everything back. final solution. Last one, 0.005 molar. And we're just going to zoom in on the middle one. Okay. Let's go to 30 milliseconds for 50 milliseconds. Go to 70 milliseconds. Milliseconds. 90 milliseconds. So we're getting very close. Let's see what 100 is. Okay, let's do 110. Pretty much nothing. So let's go to 111 maybe. $110.5. That's pretty much nothing, so let's just call it. So null is about 110. That's more like it. And let's increase tau to make sure the signal goes back up. So I'm at 200, it goes back up. Keep getting higher as I increase tau. Yep. Okay, so it definitely goes back up. So that's the end of experiment 4. Maybe I'll come back with some explanation for why it doesn't do what we expect, and maybe I'll also be back to explain some of the things you have to do on the lab report, but I think it's pretty straightforward and much of it we covered in the introduction. So there's no error analysis, but you should answer the discussion questions, a lot of which I went over in the introduction. So number 2 I didn't really talk about, but that's an interesting question, and I think you can answer that on your own. For calculations and data, All we're providing you is that first 90-degree pulse acquire experiment, so that should be in your lab report. Show all the plots that you have to do, like I showed on the board, those plots of for the T2 experiment and the plot for the T1 experiment, so that's the amplitude of magnetization versus tau, and along with the one for experiment 4, 1 over T1 versus the concentration. And you should also find T2 and T2 star based on that experiment 1. And I think I'll be back if I have anything more to talk about for the lab report. So that's it for now. Hello, so this is part of experiment 4. And in the first part, we got results we didn't expect, and I said that I would talk about that. So this is actually after the part where we got the bad results, proceeding where we're doing the experiment again and getting the results we expected. So use the data from the section of the video that is after this for experiment 4. So where you should see the relaxation times and the tau nulls decreasing with the increasing concentration of the copper ion. So we put the incorrect one there because we want the video to feel like you're actually there with us, like you're a member of the lab group, you got something you didn't expect, and in that situation, when it's so clearly incorrect, you would ask the TA, and the TA would probably just tell you to do it again and be careful. So when you see the incorrect results, think about what could have gone wrong to produce those results. If you could see clearly that something was done correctly, then that did not result in the incorrect results. So if you notice anything, that's where you should write about that in the error analysis. So think about things like the making of the solutions, or think about the volume of sample in the NMR tube. Things like that. It's not an instrumentation issue, so so these are the type of things you should talk about in the error analysis that might have led to the incorrect results. So now pay attention to this correct version of experiment 4 and use the data there in your lab report. All right, the final experiment, I'm going to keep all my parameters the same from the beginning of experiment 3, because we're just doing the same experiment but with different concentrations of copper ion. So my first pulse is still the 180-degree pulse, my second pulse is still the 90. Tau I set back to 20 milliseconds because we're going to want to go to higher taus to go through where there's no signal here in the middle, and then increase the tau back up so we get higher signal, and back to 1, p to 10. So all I'm going to do is repeat 4 more times what I did in experiment 3, this time with the solutions we just made. And that pretty much covers it. And what I'm expecting to see is that since we found the tau null for pure water yesterday, which was about 1 second, somewhere in that range, the greater the concentration of copper ion that we add, the smaller that tau null should get. So we don't have to go step by step like we did for experiment 3. I'm just gonna go quickly through it. See the signal decrease. See where it hits 0. Note that, and then increase it back up. Increase the tau so we can see the signal go back up, just to confirm that we have the correct tau null. So the first solution is the 0.00125 molar of copper ion, and I'm starting tau at 20 milliseconds. So I'm just going to move the cursor along with where the maximum is, and I'm going to continue to zoom in so that we can get a nice null when we get there. I'm going to increase it to 40 milliseconds. Now 60 milliseconds. 80. 100 milliseconds. Let's go to 150 milliseconds. So we can already see that it's decreasing much quicker than just the pure water, so that's good. So the copper ion is making the relaxation happen quicker. And I'm gonna keep zooming in a little bit. (180 milliseconds). (200 milliseconds). (220). 250 milliseconds. 280 milliseconds. So as we approach the null, I'm going to try to go in smaller steps. And keep zooming in. 300 milliseconds. 320. 330. 340. 350. 360. We're getting pretty close. 370. Well, let's go to 380. 390. 400. It's somewhere around here. I think 400 is even less. So let's go to 410. Like, clearly we can see that even at 410 it goes back up. So I'm going to call tau null for the 0.00125 molar solution about 400 milliseconds. And I'm just going to go up to 450. And it goes back up. 470. It gets even greater, so that confirms that we passed through the null, and that's it for the first solution. So I'm just going to put my tau back to the 20 milliseconds and then zoom everything back out so we can start on the second solution. So the second solution should have a tau null that is somewhere less than 400 milliseconds, so it won't even take as long to find it as the first solution did. And I'm going to change samples. So off camera, I put 100 microliters of each solution into different NMR tubes. So here. So all four I just put over here. And I use the same pipetter. And I was just made sure that all of that volume was occupied at the bottom of the tube, because if some of it gets stuck to the sides, it won't be in the actual NMR coil. So there might be parts of like the NMR coil that have the solution we want to measure the signal for, and parts that don't have anything. So we want the whole NMR coil to be filled. So I made sure that everything was at the bottom. So the next solution, this 0.0025 molar, going to increase to 50 milliseconds. And I'm going to zoom in. And again, I'm just going to wait until there's no signal, and then go through it and go back up. 70 milliseconds. A 100 milliseconds. One 20 milliseconds. On 40 milliseconds. On 60 milliseconds. So we're already getting pretty close, so that's good. This should be less than 400. Let's go to 180 milliseconds. $200 milliseconds. Okay, so I'm gonna keep zooming in, try to get the exact null. So we're very, very close. 210 milliseconds. 220 milliseconds. 230 milliseconds. So I think it's, so 230, it goes back up, so I'm gonna call it about 220. So for 0.0025 molar, the tau null is about 220 milliseconds. And I'm just gonna bring it back up to confirm that the signal goes back up, so at 250 milliseconds. The signal is already much larger. And at 300 milliseconds. So it definitely goes back up, so it went through the null. So I'm going to bring the tau back to 20 milliseconds and go on to the next solution. So this is the 0.00375 molar solution, and its tau null should be less than 220. So let's go to 40 milliseconds of tau. Milliseconds. So we can already see that signal decreasing very quickly. 80 milliseconds. Hundred milliseconds. 120 milliseconds. 130 milliseconds. 150 milliseconds. 160 milliseconds. So we're getting very close. I just zoomed in a lot. So I think it's going to be about there. Let's go to 170 milliseconds. We can see no signal that we can distinguish from the noise. So it just went up at 170. And let's just call it 160 milliseconds. Okay, and then bring the tau back to 20 milliseconds. And let's do the final solution. So the final solution is 0.005 molar, and we expect its tau null to be less than 160 milliseconds. So let's go to 40 milliseconds. 60 milliseconds. So again, we're going down very, very quickly, so that's a good sign. $80 milliseconds. $90 milliseconds. 100 milliseconds. 110 milliseconds. So I zoomed in a lot so that I could see the noise looks more like this, and the signal we can still see a little bit there at the end. 120 milliseconds, and when I can't see any signal in the noise, I know I've reached the tau null. So we're probably pretty close to there. 130 milliseconds. Okay, so that went back up. So let's call it about 120 milliseconds for the 0.005 molar solution. And that's the end of experiment 4. And we'll be back to go over the requirements for the lab report. So that's it. Everybody, hopefully this is working okay and you can hear me. So now I'm back home, and hopefully you are all home too, watching this and being safe. And I'm just going to use some of this time to go over what I want to see with the lab report, so you know what we're looking for when we grade. Because we don't want you to have put a lot of effort in the lab report, but then not include some of the basic stuff we want and have to take off points for that. So, this is Kevin again. Chalik, that's me. And so hopefully you turned in the first couple of lab reports already and maybe got one back, so you sort of have a feel for generally what we're looking for in the format, but I'm going to go over it as much as I can to try to minimize any mistakes you might be making. So the first thing is the introduction, and hopefully you can read all of this okay, because I'm writing on my computer with a fat computer writing pen thing. The introduction should be about 1 to 2 pages, and you should have 3 sections: purpose, procedure, and theory. So for the purpose, that should be pretty short, maybe a couple sentences to a paragraph. Why are we doing this experiment? That's a very big question. You're doing the experiment because it's part of one of the courses you're taking, but I want to just connect some of the ideas that we talked about to the concepts of magnetic resonance. So NMR and MRI. So what's important about magnetic resonance, and why does that help us, and why is that important to understand? So you can just briefly describe that. And then the procedure. That's straightforward. That's just what we did in the experiment. So it can be a list of steps, or a paragraph or two. However, you're not just copy and pasting exactly what was in the lab manual. That's too long anyway. It should be just a brief, hit the key highlights. I don't want it taking up too much space. And you also should write out what we did in the video, not the lab manual. So obviously it's going to be pretty similar, but it's not exactly the same. So yeah, so you're going off more based on the experiment we did in the video. And again, keep it brief. I don't want that to take up too much space. And everyone's going to have very similar things, obviously. And then theory. So this will be the bulk of the intro. And that's where hopefully you're going to talk about some of what Professor Bardeen talked about in the lecture, some of what Manpreet and I went over during the lab, and some of what was in the lab manual. And you'll start to put all of those together with what we did in the experiment. So there's a lot of stuff you could talk about. You don't necessarily have to talk about all of the things I'm going to list, but it's the type of stuff you should be thinking about as you're writing this section of the lab report, and include whatever you feel is the most important. But if you can hit on like all of these ideas, that would make for a really good theory section. And again, that should be the bulk of the introduction. So maybe the theory by itself will probably be nearly a page at least. So spin states, alpha and beta would be good to talk about. And the energy levels between them, the delta E. Part of what's gone over in lecture. Of course, T2 star, T2, T1, and the difference between them and the experiments we do to find them. That's basically what the lab is. And this doesn't have to be like a detailed description. Obviously, I don't expect any student, undergraduate, to know everything about these experiments, but I just want to see like an expression of knowledge. Like you put some thought and effort, you watch the videos, you understand the basics of what's going on. Basically, just use what you know, even if it's not that much, to describe how you think these experiments work. And so something else that would be useful to talk about is pulse length. Okay, when we adjust the length of the pulse during the experiments, what is a 90-degree pulse, what is a 180-degree pulse, and what do we use those for? And then also, it would be good to point out if this is a lab where we talk a little about MRI, and basically the last part of the experiment is all about the addition of ions. So how does the addition of ions change T1? Comment on why this happens. Because that's an important part of this experiment, and it's something you'll have to talk about later in the lab report in the discussion with experiment 4. So it'd be good to start thinking about that here. What do you expect to happen as we add ions, and what do you expect to see from the chart you're going to make? And then maybe the last good idea would be just equations. What are some of the equations you're going to be using? How do you derive those equations? If you look in the lab manual, you'll see some, and just to start thinking about those, what those equations, which experiments those equations go with, what do each component of those equations mean? So if you're able to hit on all of those points, that should fill the introduction quite well. And if there's other things that you notice in the experiment that you might want to put in the introduction and talk about the theory for, that's a good idea. But if you hit on all of those, that would make for a very nice introduction. Okay, the next section will be data and calculations. So for this, you should really include all the data we took from the experiment in tables or graphs. Like as much data as you can stuff into this. There's really not too much with this experiment. However, maybe we mentioned this while recording in person, that for experiment 1, we have the envelope of the FID, and that should be posted with this video on iLearn as a CSV file. But the other experiments we did, me or whoever doing the experiment just called out the value that we were getting at each point. And for those, we're actually not going to post online, so hopefully there's no confusion over that, because you should pretend you were in there doing the experiment with us, writing down that data in your lab notebook, and that's what you should be doing at home. And luckily it's a video, so if you didn't do that, you can go back and you can fast forward through all the dead time, write down the data points you got, and I'll go through those during the experiments, what you should have been writing down. So for experiment 1 data, you'll have to import this file as a CSV to Excel. Sometimes students have problems with that. So if you do, send me an email and I'll send you as detailed instructions as I can get in order to do that. But what you're looking for is this envelope of the FID. FID. And when you do that option in Excel to import a CSV file, it'll allow you to basically like pick which data points you want to use and how to use them. And then once you have the data, it should be voltage versus time, and then you just graph that, and should look something like this, like what we saw in the scope. So V for voltage, time will probably be in seconds or milliseconds, and it looks something like this. You should remember from the experiment. Right, so that's our envelope. So we're going to use this data from the first experiment to extract T2 star. Just the pulse acquire doesn't refocus any of that field inhomogeneity, so this is the experiment we used to find T2 star. In order to do this, we actually take the natural log of V, and we just want this area here, really after the pulse occurs and we have that decay, and what that will result in. Now we do natural log of V versus time is a linear line, so in the form y equals mx plus b, and you should use Excel to fit this line as well. So you'll have all the data points here, so it might look something like this with all the data points, and then the line through it will, if you ask Excel to fit it for you as a linear line, it'll produce that line, and then you can also ask Excel to do y equals mx plus b. I'm sure a lot of you have done similar things before. And so this m, this slope, will help us find T2 star. So T2 star is actually 1 over that slope times 10 to the 3, and that'll get you T2 star in milliseconds. Okay, so that's the data for experiment 1. I want to see 2 graphs, one that's just right from the scope, and the other that's turning it into this linear line with the fit, and then the calculation for T2 star. And then you should also put down the pulse length. So that'll be A length, whatever setting we put that at. Did we use? And that's the data for experiment 1. And now for experiment 2. Again, because now we're using the 180-degree pulses, I want you to write out the pulse lengths. Not just pulse length, I'll say what parameters did we use? So that's pulse length, period time p, tau. We adjusted those obviously. So what I want to see is a table of amplitudes and tau. It would actually be good. Amplitudes, tau, and 2 tau. Again, this is data I said out loud as we were recording the experiment, so you should be writing the table as I'm going through the experiment, and then put that data table in the lab report. And the reason we want those is because you're going to construct the graph of amplitude. The amplitude is again in volts versus 2 tau. So when we were doing the experiment, we were just adjusting tau, so just keep that in mind. I definitely mentioned it a few times, like tau is whatever, so that means 2 tau is this. So you should know what both are. And it should produce a curve that looks something like this. And again, you're going to have the data points and have Excel fit it for you as an exponential fit. So that'll be in the form of y equals a to the e bx. And to find the real T2, that'll just be 1 over b, and times 10 to the third, and that'll be T2 in milliseconds. So you can see the calculations are pretty straightforward so far. Just hopefully you don't have any issues converting that data into Excel. And so for experiment 2, I just want to see the data table for the data I said out loud, the graph of that data, amplitude versus 2 tau, not just tau, and then the calculation for T2. And then for experiment 3, again, we said the data out loud, so I'd like to see data table of the amplitude in volts, versus tau as we adjusted it. So this is where your data and calculations will get a little tricky. For this experiment, your data won't look perfect. So what it should look like, ideally, is amplitude in volts versus now just tau. And it'll look something like this. Again, it won't look perfect. But you should be able to, just by inspection, or if you can figure out how to get a good fit of it, you use that to find T null. So that's that spot right here. And that's the value you want to use. Not T null, tau null. And remember, when you're building this graph, all these amplitude values we reported as positive. But as you're leading up to the tau null, we just know that they're negative, and as you pass the tau null, we consider them positive. So it says in the lab manual, it might be a good idea for some of these values that are very close to tau null, and we don't know whether they're necessarily positive or negative, you can leave them out if you still get like a decent looking curve. Okay, so remember to do that. You don't want to consider all the values positive. You won't get something that looks like this. And then you're going to calculate T1 from tau null. And I definitely talked about that in the first part of the video. But you should derive what we're going to use. So derive that T1 is about tau null over the natural log of 2, or about what I said at 1.44 about times tau null. Those are the same things. But you should, I think, don't just write that. We're actually deriving that from this equation. The magnetization in Z equals then null magnetization times 1 minus 2 e to the minus 1 over T1. Times tau. That should be tau. And this is also in the lab manual, so it starts that derivation a little bit. It's pretty straightforward. You can see where you should see where the natural log comes from and what values you're going to put in those places. So look at the lab manual for how to start that. It should be fairly straightforward. And then make that calculation for the T1. So for experiment 3, I want to see that data table. I want to see this graph, amplitude versus tau, the derivation of this equation to find T1 from tau null, and then the calculation to find T1. I'm trying to be careful about when I say T and when I say tau, because they're different things and it can get very confusing. Okay, so hopefully that made more sense. And that's all I need to see for experiment 3. Again, this is where it gets tricky. Your graph is just not going to look perfect, but you should be able to see where the tau null is. And then the calculation is fairly straightforward, and the derivation is mostly given to you in the lab manual. Now for the experiment 4. Right. So I want to see the data table. Of the concentration of copper ions. The tau null associated with those concentrations at the experiments I did. Wow, I drew another T. Sorry. Tau. And then the T1 times. So just 1.44 times the tau null of that. And then you're going to draw the graph of 1 over T1 versus the concentration of the copper ion. And so 1 over T1 will be inverted seconds versus the concentration of copper ion in molar, and that'll look something like this. Again, you'll have the data points. You'll just have to do the fit in Excel. And then you're actually going to have a second very similar graph. So not just the concentration of the copper ions in molarity, but also find concentration of copper ion in per centimeters cubed. So think about, in order to do this, that concentration and molarity, what we just did initially, is moles per liter. And then use Avogadro's number. So that should help you convert from number of moles of copper ion to just the number of copper ions, and volume conversions. So that should help you convert from liters to centimeters cubed. And then you're going to have another chart, still 1 over T1, but now it'll be concentration of copper ions in number of ions per centimeter cubed. And that'll still should give a linear fit. So you're going to have these two graphs for this. And then it goes over in the lab manual and the lecture how you're going to use these linear fits. So you should get, sorry, that is messy. So you're going to get linear fit for both, y equals mx plus b, and you're going to find the k for that. That's the relaxivity constant. So this is going to be the most involved calculation. Find k in lab manual and lecture. And then you're also going to find C. This is also in the lab manual. And you're actually going to, for both, oops. Okay, so let me clarify that. For both the graphs you put, you'll get two different linear fits, and you're actually going to find the value of K and the value of C for both of those graphs that you get. And so to find C, it tells you K equals C times the viscosity over the temperature. So for this is the viscosity. Assume the viscosity of water. Because even in these solutions, it's mostly water. The concentration is very small. And for T, now this time this T is temperature, not T1 or T2 or tau or anything like that. It's just temperature. Assume room temperature, RT. Okay. And for the viscosity of water, that you'll have to look up. So you'll just look up the viscosity of water, find it in convenient units, and then cite where you got that value in the references. So that's for experiment 4. Definitely the most involved. So you need the data table of the copper ion concentration that we gave to you during the experiment, the tau null that we found for each, and then the T1 based on your calculation using tau null. And then you're going to have two graphs of 1 over T1 versus concentration of copper ion. One of the graphs will just be the molarity of the copper ion, the other will be copper ions per centimeters cubed. And I went over a little bit how to go between those. And then for both graphs, you're going to find K and C. So that's what I want to see for experiment 4. So there should be 2 values for K, 2 values for C, depending on which graph you used. Now, also in the lab manual, it wants you to do a couple more calculations. So this should also be in the data and calculations section. We're going to calculate BC, static magnetic field. This was definitely gone over in lecture, but I'll just help you get started. And part of why I wanted you to think about the difference in energy between the alpha and beta states in the introduction is because that's what we're going to do here. Because if you remember, the difference between those states is the Planck's constant times gamma times the static magnetic field that we want. And so in order to find the calculation of BZ, remember that omega is the Larmor precession frequency. And remember, during the experiment, when we set the frequency, we started at 21, but we discovered that it was closer to, let me make sure I give you the correct number. It was closer to 21.062 megahertz. Okay, and that equals gamma times BZ. Okay, so that should help you get started, and you should also know what gamma is. Obviously, that would help. So gamma is the gyromagnetic ratio. Very important concept in magnetic resonance. It's a number that's different for every particle. In our case, in NMR, it's different for depending on the nuclei that you're using. So we're doing proton NMR. So proton is 1H. So you need to find the gamma for 1H. So we usually write that something like this, gamma of 1H. And that you'll need to look up, again, similar to the viscosity of water. Look up that value and then put in the references where you found it. Make sure you're using the correct units so that B is in units of Tesla. And if you have any trouble with the calculation or trying to find what gyromagnetic ratio to use or anything like that, please email me or come to my office hours or during the lab sections. Me or Monpreet will be online. So that should help you get started with that. He also went over it in lecture. A little more difficult is finding the other calculation, which is the induced field Bx. So to induce a field along Bx, remember that we apply a 90-degree or pi over 2 pulse. Those mean the same thing. We use those pretty interchangeably. To induce field along X. And to help you get started with this one, that pi over 2 in radians. is equal to gamma, the same gyromagnetic ratio for hydrogen that we just used, times Bx, that's what we're going to find, times the pulse length. So in this case, this is the length of our 90-degree pulse. So not necessarily A, because we did an experiment where A was 180, but this is the length of our 90-degree pulse. So that should give you what you need to find Bx. Again, it should be in Tesla. So you should use, knowing that the field for both these calculations should be in Tesla should help you determine whether you did the calculation properly. Your units should cancel out and combine in the correct ways to end up with an answer in Tesla. Alright, so that was the data and calculations. That'll take up a lot of space for the lab report, so that should be the majority of it with all those graphs and data tables and all that. And then we'll have discussion and error analysis. And this will be about 1 to 2 pages. So for this, you should find literature values. Again, you're going to be looking these up and comparing, and whatever you're using for your literature values, wherever you got that, you're just going to put in the references so I know where you got it. And this shouldn't be too hard to find online. For T1 and T2 of water, because that's what we did in the first 3 experiments. We're finding the T1 and T2 of just water, and then you're going to find the percent error. So compared to experimental values. Oops. So compared to experimental values, using percent error. Alright, so I'm definitely going to be looking for that. Obviously, not going to take off if you have a large percent error because you didn't do the experiment, but if you did the calculation incorrectly or you do the percent error calculation incorrectly, that I'll notice. But if you did all the calculations correctly and you happen to end up with a large percent error, that speaks more to my failings than yours. And then just discuss and explain your results. So there's a lot you could talk about here. Basically, do your results make sense? Are you getting T1s and T2s that are along the millisecond or second time scale? Or are they in like hundreds of seconds? Or are they in like nanos of seconds? So think about whether those values actually make sense. And a good thing to think about, which we'll also talk about later, like an example is T1 larger than T2? Because as we've gone over in lecture and I talked about at the beginning of the lab, T1 should be much larger than T2. If you calculated your results and you didn't get that, can you come up with some explanation as to why? So it's not enough to just say like, well, this didn't make sense or this made sense. You more have to explain. So yeah, and then for error analysis, there's no actual like, you don't have to do like any standard deviations or any of that stuff, but I more want a source of errors or a source of possible errors. So pretend like you're watching the video and pretend you're there, like this is your lab group and just someone else is doing this part of the experiment. So like if you saw me do something incorrectly, which is I'm pretty sure I did it as well as I could, but if like you said, oh, if you saw me do something and you're like, oh, I don't think that's right, this is the place to put it. So if you saw something done incorrectly, just point it out. And what could be the result of those errors? If you didn't see anything that I did incorrectly, then there's still some stuff you can talk about. So maybe some possible errors. So something to think about is, I only talked about it briefly, but it could end up mattering a lot, is how we only fill the bottom 5 millimeters of those little NMR tubes. So why is that? Well, the sample needs to be a certain distance and fill up enough space in the actual spectrometer compared to the size of the coil. So if we didn't fill up, like maybe you didn't get a good look at it, so you're not even sure, like, did I fill up the correct amount of the NMR tube? How could that affect your results? Another thing to think about that we'll also talk about during the questions is, what if the pulses are not calibrated correctly? Like I talked about, like, it's very difficult to get, doing this experiment, to get these exact 180 or these exact 90-degree pulses. So if you noticed something and you thought maybe one of the pulses wasn't calibrated exactly right, what's the result of that possible error? So this is a good place to talk about that. So that's the discussion and error analysis. And the next section is questions. So there's 3 questions in the lab manual. And these will hopefully get you thinking. So the first one, actually, we talked about this a lot. So from the lecture, from the lab manual, from what I talked about throughout the lab, you should, let me just get the actual questions out. So it's basically, again, you're just describing T1, T2, T2 star. Did the experiments you did the results you get from the experiment correspond with what you expected? So in fact, this is probably something you talked about either in discussion or the intro or something. So you should really provide a nice answer here, a nice solid paragraph. And it's a good idea to give definitions of T1, T2, T2 star, even if it's just repeated information you gave in the introduction. So this is a good spot to sort of connect, like, the theory of this from the introduction with what you actually did in the experiment. So not worried about this one. I'm just going to say that we talked about this a lot. So there's plenty to say there. Number 2, actually, we did not talk about so much. This is the question about the sensitivity of NMR and compared to other spectroscopic methods. So that's good, because instead of just like going back to the lecture, watching that 5 minutes of the video again, you will hopefully really think about this. So think about how this change in structure change signal in NMR and the other methods. So hopefully that'll get you started if you're not sure. And with regards to the sensitivity of NMR, I can talk about that a little bit, so also hopefully this will help you. When you're observing NMR, these alpha and beta states, we know that this energy difference is equal to the gamma times Planck's constant times the magnetic field, I'll call B naught. It turns out that this population difference, so it turns out that this transition is extremely small. Small e energy transition. This is important to think about because this results in a small population difference between the states, alpha and beta. Small population difference between states alpha and beta. And this matters because the sensitivity of NMR is proportional. Is proportional to that population difference. So that should tell you about the relative sensitivity of NMR, and then you can think about these other methods that you know about as well. And this also gets into a little bit about why that gamma value is so important. The proton, the hydrogen, actually has a relatively high gamma. When you look up the gyromagnetic ratio of the hydrogen atom, you'll probably also see values for some other NMR active nuclei, like C13 or N15. Those are the other extremely common nuclei we look at with NMR. And the gyromagnetic ratios of those are actually significantly less than the hydrogen. So hydrogen is actually a relatively sensitive nuclei, but depending on what you're looking at, it gets less and less sensitive. So that's why proton, hydrogen, NMR is much more common, and carbon, NMR, nitrogen, NMR are much less sensitive because of the gyromagnetic ratio. So hopefully that a little bit of that information will help you think about what to write for number 2, and then the third question. This one. So this is part of what I wanted you to think about in the discussion. I mentioned this. If you don't have the exact right length of the pulse, so I'll just say that we talked a little bit about this. And again, I'm curious what people write, so I don't want to say too much. But I definitely said, if you really understand what the length of the pulse means and what we're doing with the 90 and 180 degree pulses with these experiments and how that helps us measure T1 and T2 and all that stuff, if you really understand it, hopefully you'll really express that with this third question, and you'll be able to write like what happens if you don't have an exact 180 degree pulse. Okay, so hopefully that covered the questions well. And then finally we're going to have the references. Don't lose points by not including references. Honestly, do it in whatever format you want, just be consistent. And you should, at the very least, reference the lab manual. So that's one, because you're all absolutely using it. And then you'll have other references for some of the constants you looked up. So we're just put where you got them. Don't use Wikipedia. You did not get them from Wikipedia. So find out where you got them. And then if you looked up any other references while doing this experiment, please include them, because you actually used it, you used the information from that source, and just throw it in the references, because sometimes I see people write things and I'm like, where did they get that from? But if it's listed in the reference, I can go back and see where you got it from. So yeah, if you're just looking up something for the introduction or a concept you're not quite sure about, and you find like an actual journal article, it would be good. But whatever you're using, if it's like another university's chemistry website, stuff like that, throw that in the references if that's what you're using to try to understand this experiment. And then, so that covers the lab report. So I'll talk about a little about just the organization. Like, I will take off points if it's badly organized. So I want to see an introduction, clearly labeled where your purpose, procedure, and theory begin. And then I want to see the data and calculation sections, and clearly labeled where you put your data and calculations for experiments 1, 2, 3, and 4. And then I want to see the discussion and error analysis section, like clearly marked, so bold or underlined or whatever. And then the questions section, and then the references section. But also in general with organization, like it should be well written, well organized. Pretend you're turning this into like an English professor. So if it's not written well, it's difficult to understand what you're trying to say. So I don't want to take off points because you know what you're doing, but you don't know how to word it correctly or something like that. So just be careful, take your time, and be well organized with it. So you don't want to lose easy points. So that really covers, hopefully in pretty great detail, what I want to see in the lab report. Please, again, I'll just write my email, even though it's everywhere in the syllabus and online, and so kchal003 at ucr.edu. Please, if you're stuck on something in the lab report, just send me an email and I'll get back to you as soon as I can. So you don't want to get stuck on something and not be able to find someone to help, because we're all just stuck at home, so it's not like you can just pop into whatever. But also, don't hesitate to ask somebody else in the class. Obviously, don't turn in the same material. You're all going to have the same data anyway, but I'll be able to tell if you obviously did the calculation with someone, especially if you both get it wrong. So, but if you're just stuck on a concept, like it can be good to talk it over with another student or the TA. So I'll have my normal office hours and also be online for the lab sections. So there's no excuse if you are getting to this early enough. Okay, so I think that about covers it.